Hello there, and welcome to the Sleepy Space Channel. 1 trillion years from now, the sky is still full of stars. What is gone is the evidence. Every galaxy beyond our own will have been carried past a horizon that light cannot cross, and the faint glow left over from the beginning of the universe will have stretched past anything an instrument could register. Anyone looking up from a world in that future would measure everything correctly and conclude that the universe is a single island of stars, static and eternal, and that they can see all of it. Tonight we move slowly through that sky, the last galaxy, the small red stars that outlive everything else, and the one clue that survives. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. The light we are talking about is still arriving tonight, and it will keep arriving for a very long while. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fall away behind you. Let's begin. Part 1. The size of the number. The universe is a little under 14 billion years old, and that number is difficult enough on its own. It is old enough to contain every star that has ever formed, every galaxy that has ever assembled, and the entire history of this planet with room left over. It is the number astronomers use as the outer boundary of everything, the full span of time in which anything at all has happened. 1 trillion years is roughly 70 times longer than that. The proportion is worth sitting with for a moment, because it does not behave the way intuition expects. Everything that has ever occurred in the history of the universe, the first light, the first stars, the slow gathering of gas into galaxies, the formation of the sun, the cooling of the earth, the entire fossil record, every civilization that has ever risen, occupies less than 1.5% of the interval this video describes. If the whole of cosmic history so far were a single day, the trillion years ahead would be something close to 10 weeks. The day would be over before breakfast on the first morning. There is a second comparison that lands even harder. The Sun has existed for about 4.5 billion years, which is roughly a third of the current age of the universe. At the moment we are describing, the cold remnant of the Sun will have been sitting in the dark for something like 200 times longer than the Sun ever shone. The bright phase of a star's life, the part we think of as the star, turns out to be a brief episode at the beginning of a much longer stillness. And yet the most surprising thing about 1 trillion years is that it is not the end of anything. This is the point that has to be established before the rest of the video can work. 1 trillion years is not the final darkness, not the last light, not the closing page. The smallest and dimmest stars in the universe will still be burning for roughly another 100 trillion years after that date has passed. The stellar age of the universe is not over at 1 trillion years. It is not even close to over. Measured against the full lifetime of the last stars, the universe at 1 trillion years is barely past its first afternoon. So the question is why that particular date is interesting at all, and the answer is that it marks the moment when the sky finishes changing. Almost every large-scale process that reshapes the appearance of the universe will have run to completion by then. The galaxies nearby will have finished merging. The galaxies further away will have finished leaving. Star formation will have effectively stopped. The remaining stars will be the ones that are going to be there for a very long time. What is left is a stable configuration, a sky that has settled into a shape it will keep for hundreds of billions of years afterward. 1 trillion years is not the end. It is the point at which the universe stops rearranging itself and simply persists. It is also, and this is the harder part, the point at which the universe becomes impossible to understand from the inside. That is the real subject of tonight. Not extinction, not heat death, not the last flicker of the last star. something quieter and stranger than any of those. At 1 trillion years, the sky is still full of stars, and there is no longer any way to find out where they came from. We will get to that slowly. For now, it is enough to hold the scale in mind, because everything that follows depends on it. Astronomy is a science built on comparing intervals, and most of the intervals we work with are short. The orbit of a planet is measured in years. The life of a bright star is measured in millions. The assembly of a galaxy is measured in billions. Beyond that, the numbers stop being quantities and start being categories. A trillion is not simply a larger billion. It is a different kind of statement about time. One way to make that concrete is to think about what has to happen for 1 trillion years to pass. The Sun currently completes one orbit around the center of our galaxy in roughly 230 million years. That single orbit, one galactic year, spans a period longer than the entire history of the dinosaurs. In 1 trillion years, the Sun would complete something over 4,000 such orbits, if it were still there to complete them, and if the galaxy it orbited still had the shape it has now. Neither of those conditions will hold. The stars we can see tonight will not be there. This is not a poetic statement, but an arithmetic one. Almost every star visible to the unaided eye is either large, bright, and short-lived, or nearby and ordinary. The bright ones burn out in millions of years rather than billions. The ordinary ones, the ones like the Sun, run for perhaps 10 billion years and then stop. Not a single star currently visible in the night sky will still be shining at the date we are describing. Every recognizable pattern in the sky will have dissolved and been replaced many times over, and then the replacements will have dissolved too. What survives is a class of star that most people have never seen, because none of them are bright enough to see. We will come to those in some detail later, because they are the inhabitants of that future sky, and the reason it is not dark. But it is worth naming the shape of the answer now, so the parts that follow have something to attach to. The universe at 1 trillion years is a single galaxy, sitting in complete and permanent isolation, filled with small red stars and the cold remains of larger ones, and surrounded by a darkness that contains no information at all. Each element of that description takes some explaining, and each of them arrives by a different route. The single galaxy is the result of a merger that is already underway. The isolation is the result of an expansion that is already accelerating. The small red stars are the result of a fuel economy that has been running down since long before the Earth existed. The darkness is the result of a horizon that already exists and is already carrying things across it, one at a time, tonight, while we speak. That last point is worth pausing on, because it changes the character of the whole subject. None of what follows is speculative in the way that time travel is speculative, or in the way that questions about what came before the beginning are speculative. Every process described tonight is a process that has been measured and is happening now. The expansion is measured. The acceleration is measured. The approach of the neighbouring galaxy is measured. The decline in the rate of star formation is measured. The lifetimes of small stars are calculated from physics that is tested daily in the laboratory. What we are doing is not inventing a future. We are letting known processes run forward and describing what they leave behind. There are genuine uncertainties, and it is worth being honest about where they sit. The behavior of the energy that drives the acceleration is not fully understood, and if it changes character, the picture changes with it. Some questions about the stability of matter over enormously long intervals remain open. But those uncertainties bite hardest, at intervals far longer than 1 trillion years. For the span we are describing tonight, the physics is on reasonably firm ground. So the arithmetic gives us a date, and the date gives us a sky. 14 billion years of history behind us, 1 trillion years ahead, and a universe that will spend most of that interval looking almost exactly the same as it does at the end of it. There is something restful in that, once the scale stops being alarming. Most of time is not eventful. Most of time is a long, slow, largely unchanging stretch in which nothing much happens and nothing much needs to. We are living in the brief and unusual part. The part where galaxies are still forming, where bright stars are still being made, where the sky is still crowded and still changing and still full of things worth measuring. It does not feel unusual from the inside because we have nothing to compare it against. But by every measure of duration, the era we occupy is a narrow band of activity near the very beginning of a long quiet. And the quiet is not empty. That is the thing worth holding on to as we move forward. When people imagine the far future of the universe, they usually imagine a void, a cold nothing, a black expanse with the lights switched off. That picture is wrong for the date we are describing, and it is wrong in a way that makes the truth more interesting than the imagination. At 1 trillion years there are stars. There are planets. There are systems that have been stable for longer than the current age of the universe, orbiting quietly, with skies of their own. There is simply no way, from any of those skies, to find out that any of the rest of it was ever there. Part 2. When everything nearby becomes one thing. Before the sky can empty, the local neighborhood has to finish assembling itself, and that process is already in motion. Our galaxy is not alone. It belongs to a small collection of galaxies bound together by gravity, a group containing 2 large spirals, 1 smaller spiral, and several dozen dwarf galaxies of various sizes. This collection is called the local group, and its total extent is something like 10 million light-years across. On the scale of the universe, it is a very small structure. The most important fact about the local group is that it is gravitationally bound, and understanding what that means is the key to everything that follows. The expansion of the universe does not act inside systems that are held together. Space is not stretching apart the atoms in your hand, or the orbit of the Earth around the Sun, or the orbit of the Sun around the center of the galaxy. Gravity within a bound system is enormously stronger than the tendency of space to lengthen, and the bound system simply holds. Expansion operates between systems, in the wide gaps where nothing holds anything else. So the local group stays. Everything outside the local group leaves. That single division determines the shape of the entire future sky, and it is worth stating plainly before we look at either half of it. The staying part happens first, and it is not a peaceful process, though it is a slow one. The 2 large spirals of the local group, our own galaxy and the one nearest to it, are approaching each other. This is one of the few large galaxies in the sky that is moving toward us rather than away, and the measurement of that approach is one of the more reliable numbers in extragalactic astronomy. The 2 will meet in something like 4 to 5 billion years. The word collision is misleading here, and it is worth correcting immediately. When 2 galaxies meet, essentially no stars strike one another. The space between stars is so much larger than the stars themselves that a direct hit is close to impossible even in a full encounter. If you scaled the Sun down to the size of a grain of sand, the nearest similar grain would be tens of kilometers away. 2 clouds of such grains can pass entirely through each other and never touch. What actually collides is the gas, and what actually reshapes the galaxies is gravity. The encounter is not a single event either. The 2 galaxies pass through each other, swing apart under their own momentum, slow, turn, and fall back together. The process repeats, each pass tighter than the last, each pass costing the system some orbital energy. Over the course of several billion years, the 2 spiral disks are pulled apart, drawn out into long streams of stars, and eventually scrambled into something that has no plane at all. What remains at the end of it is a single elliptical galaxy. This is a genuinely different kind of object from the one we live in now. A spiral galaxy has a flat disk, spiral arms, a defined plane of rotation, and lanes of gas and dust where new stars form. An elliptical galaxy has none of these. It is a smooth, roughly spheroidal swarm of stars on randomly oriented orbits, thinning gradually from the center outward, with no structure to speak of. The consequence for the sky is immediate and quite beautiful in its own way. From inside a spiral galaxy, we see a band of light across the sky, the combined glow of the disk seen edge-on from within it. That band is the reason our galaxy has the name it does, and it has been a feature of the sky for the whole of human history. In an elliptical galaxy, there is no band. Stars are spread more or less evenly in all directions. The night sky from a world in that future galaxy would be softly uniform, with no lane, no structure, and no obvious pattern. The merger of the two large spirals is not the only thing that happens. The third spiral of the group falls in as well, and behind it, the dwarf galaxies, one after another, over tens of billions of years. Small galaxies orbiting a large one are gradually stripped of their stars by tidal forces, drawn out into streams and absorbed. This process is happening already. Our galaxy is currently taking apart several small companions and has done so many times before. Over the next 100 billion years or so, the process finishes. Everything in the local group ends up in one place. There is a final burst of star formation associated with the merger, and it is worth describing because it is the last one. When two galaxies rich in gas meet, their gas clouds do collide, and the collisions compress them. Compressed gas collapses, and collapsing gas makes stars. The merger produces a surge of new star formation across the combined system, bright and comparatively brief. It is the last great generation of stars the region will ever produce in that way, and it consumes a great deal of the remaining fuel. The globular clusters go too, more or less. These are the ancient, tightly bound spherical swarms of stars that orbit in the outskirts of galaxies, each holding hundreds of thousands of very old stars. They are among the oldest structures in the universe, and over long enough intervals, they slowly evaporate. Stars drift out of them one by one until the cluster dissolves. Those that survive evaporation are eventually absorbed into the merged galaxy. Either way, by the date we are describing, almost none remain as distinct objects. By roughly 100 billion years from now, the process is essentially finished. And here the arithmetic becomes remarkable again, because 100 billion years is a tenth of the interval we are discussing. For the remaining 900 billion years, nothing further of this kind happens. The local universe consists of exactly one galaxy, and it consists of exactly one galaxy for a length of time far longer than the entire history of the universe up to now. That single galaxy is sometimes given a blended name in discussions of the far future, combining the names of the two spirals that make it. Whatever it is called, it is the only structure left in the observable sky at the date we are describing, and it will remain so for an interval that makes the whole of cosmic history to date look like a preface. It is worth noticing what has already been lost by this point, before the sky even empties. The disk is gone, which means the spiral arms are gone, which means the sites of ongoing star formation are gone. The distinct identities of the individual galaxies are gone. The clusters are gone. The particular arrangement of stars that produced every constellation ever named is gone many times over. And all of this happens in the first tenth of the interval, as a kind of opening act. The merged galaxy is not diminished exactly. It is larger than either of its parents, holds more stars, and has a deeper gravitational well. But it is simpler. Structure has been traded for smoothness. The processes that made the galaxy interesting to look at, The arms, the lanes, the bright young clusters strung along them were processes of assembly, and assembly is finished. What sits at the center deserves a brief mention here, though we will return to it. Both large spirals hold a supermassive black hole at their core, and in the merger, those two black holes sink toward the center of the combined system, orbit each other for a long while, and eventually join. The combined object is larger than either was, fed by the material that falls inward during the encounter. Afterward, it settles into quiet. There is very little left for it to consume, and it spends the following trillion years mostly starved, sitting at the center of a galaxy that has stopped bringing it anything. So that is the first half of the future sky, and it is the half that gets built rather than removed. One galaxy, smooth and spheroidal, holding perhaps 1 trillion stars, its structure erased, its star formation nearly spent, and its center quiet. It is finished early, and it changes very little afterward. The other half of the sky is the half that goes away, and that process has already begun. There is a question people often raise at this point, and it deserves a direct answer. If the expansion of space is accelerating, why does it not eventually overcome gravity even inside bound systems and pull the galaxies apart as well? The answer depends on how the acceleration behaves over time. In the picture that best fits current measurements, the energy driving the expansion has a constant density, the same amount in every cubic meter of space, now and always. That produces a steady, unchanging outward tendency, and the gravity holding a galaxy together is stronger than that tendency by an enormous margin. The bound system wins permanently, and there is no point in the future at which it stops winning. There are alternative descriptions in which the driving energy grows in strength over time, and in those the outcome is different. Bound systems are eventually torn apart, and the tearing works its way down in scale from clusters, to galaxies, to solar systems, to matter itself. That scenario is not favored by the data, but it is not entirely excluded either, and honesty requires acknowledging it. If it turned out to be correct, the picture described tonight would not survive to the date we are describing. The measurements so far point the other way. The behavior of the driving energy appears steady rather than growing within the precision available. So the local galaxy holds, and the picture stands. It is worth adding one more thing about the merger before moving on, because it concerns what happens to individual stars during it. When two galaxies pass through each other, the gravitational field each experiences is changing rapidly, and stars respond by moving onto new orbits. Some are drawn into the center. Some are flung out into long streams that arc away from the merging system, forming the tidal tails visible in images of galaxies caught mid-encounter. A fraction of those stars are ejected entirely. They leave the merged galaxy on paths that never return, traveling out into the space between galaxies at speeds sufficient to escape. There are stars in the present universe doing exactly this, identified by their velocities, moving outward through the halo on their way to nowhere in particular. For those stars, the future is different and considerably stranger. Ejected before the merger completes, they drift outward through empty space with no galaxy around them. Their own expansion-driven isolation is total. Any world orbiting such a star would have a sky containing exactly one object, its own star, and nothing else at all, in any direction, at any wavelength, permanently. That may be the most isolated situation the universe ever produces. A single star, a few worlds, and a sky with nothing in it. There will be a scattering of such systems drifting outward from the merged galaxy for as long as anything lasts. Part 3. The sky empties. The expansion of the universe is not a controversial idea, but it is a frequently misunderstood one, and the misunderstanding matters here. Galaxies are not flying outward through space from a central point. There is no center, and there is no outward. What is happening is that the distance between things that are not gravitationally bound is increasing, everywhere, at the same proportional rate. Every observer in every galaxy sees the same thing. Everything unbound is receding, and the further away it is, the faster it recedes. For a long time, the expectation was that this expansion would gradually slow. Gravity pulls everything toward everything else, and a universe full of matter ought to decelerate. The measurements, when they were finally made with enough precision, showed the opposite. The expansion is accelerating. The rate at which distant galaxies recede is not declining but growing, and it has been growing for something like the last 5 or 6 billion years. The cause is not understood, and it is honest to say so plainly. The energy responsible is detectable only through this effect. It appears to be a property of space itself, present at the same density everywhere, which means that as space grows there is more of it, which means the acceleration continues rather than dilutes. That is the picture that fits the data, and it has held up against a good deal of testing. What the energy actually is remains an open question, and one that may stay open. The consequence of acceleration is a horizon, and the horizon is the central object of this part of the story. Because the recession rate increases with distance, there is a distance beyond which the space between us and an object is lengthening faster than light can cross it. Light emitted from beyond that boundary today will never arrive here, no matter how long anyone waits. Not because it is traveling slowly, but because the road ahead of it is being extended faster than it can travel. That boundary sits at roughly 16 billion light-years, and it is a permanent feature of an accelerating universe. As the acceleration continues, galaxies cross that boundary. Not all at once, and not dramatically. One by one, over billions of years, each galaxy in the sky reaches the distance at which its future light can no longer reach us, and passes beyond it. From that moment on, we are still receiving the light it sent earlier, but we will never receive anything it sends afterward. The manner of the fading is worth describing carefully, because it is gentle rather than abrupt. A galaxy crossing the horizon does not switch off. Its light stretches. The wavelengths lengthen as they travel through expanding space, so the light reddens, and then reddens past red into the infrared, and then past that into radio wavelengths measured in meters and then in kilometers. At the same time, the photons arrive more and more sparsely, separated by longer and longer intervals, because the same stretching applies to the spacing between them. The galaxy grows redder, dimmer, and slower until it falls below anything that could be detected. It fades rather than vanishes, and the fading takes an enormous length of time. The nearest large cluster of galaxies to us is not bound to our group. It recedes with everything else. The great filaments and sheets of galaxies that make up the larger structure of the universe, the arrangement that surveys have spent decades mapping, all recede. Every galaxy currently catalogued, every faint smudge in every deep image ever taken, every object beyond the local group, is on its way out. The timescale is long by human standards and short by the standards of this video. Within something like 100 to 200 billion years, no galaxy outside the merged local system remains observable by any instrument. That is 1/10 to 1/5 of the interval we are describing. By the time 1 trillion years has passed, the isolation has been complete for something approaching 800 billion years. It is not a new condition. It is the settled and permanent state of things. There is one more thing in the sky that goes, and its departure is the quietest and the most consequential. The universe is filled with a faint background of microwave radiation, arriving uniformly from every direction. It is the cooled remnant of the glow of the early universe, from the moment when the expanding gas became transparent and light was able to travel freely for the first time. That light has been traveling ever since, stretching as it goes, and it now sits at a temperature of a little under 3 degrees above absolute zero. It is the single most informative signal in cosmology. It stretches too. Over 1 trillion years of accelerating expansion, the wavelength of that background radiation grows by a factor so large that writing it out serves no purpose. Its temperature falls to a number with dozens of zeros after the decimal point, indistinguishable from nothing at all. Its wavelengths become longer than any antenna that could reasonably be built. The background does not disappear in principle, but it disappears in every practical sense. There is no measurement that could find it. And with that, the last signal from outside is gone. High-energy particles that currently arrive from beyond the galaxy stop arriving. The faint glow of distant sources stops arriving. Every channel of information from beyond the local system closes. Between the edge of the merged galaxy and everywhere else, there is simply nothing to detect. Not a dark sky with faint things in it, but a sky with no content of any kind. It is worth being precise about what that means, because the phrase "empty sky" can be misread. The rest of the universe is still there. Those galaxies still exist. They are still full of stars, still turning, still doing whatever galaxies do. Their light is still traveling. It is simply traveling through a space that is lengthening faster than the light can cross, so it never arrives, and never will. The universe does not shrink. It becomes unreachable, which is a different thing, and in some ways a stranger one. There is a symmetry to it that is worth noting. An astronomer in one of those distant galaxies sees exactly the same picture, at the same time, for the same reason. Their sky empties as ours does. Their local group merges as ours does. Everything they can see leaves them, and we are among the things that leave. Every galaxy in the universe ends up alone in the same way, and none of them can know about any of the others. So the sky at 1 trillion years is finished. In one direction, there is a single smooth galaxy, unstructured, holding its stars in randomly angled orbits, quiet at the center. In every other direction, there is nothing. No faint background, no distant light, no signal, no structure, nothing that any instrument could register. And that condition is stable. It does not develop further. It is what the sky is going to be. There is a detail about the horizon that is worth clarifying because it is easy to get backwards. The horizon does not move outward to swallow things. It sits at a roughly fixed distance while the objects themselves are carried past it by the lengthening of the space between. Nothing chases anything. The road simply grows. It is also worth saying that the objects crossing it notice nothing. There is no boundary in space at that location, no change in conditions, no local event of any kind. A galaxy passing beyond our horizon continues exactly as it was, entirely unaffected, and its own observers see nothing happen. The horizon is a relationship between two places rather than a feature of either one. And the process is not symmetrical in time. Once an object has passed beyond, it never returns. In a decelerating universe, objects that were once out of reach could come back into view as the expansion slowed and light caught up. In an accelerating one, the traffic runs one way only. Every departure is permanent, and the count of observable objects can only decrease from here. That fact is what gives the whole picture its shape. The universe is not becoming emptier in reality. It is becoming emptier in view, monotonically, at a rate that has already been measured, with no mechanism available to reverse it. Which brings us to the part of this that is genuinely difficult, and that no amount of gentle framing entirely softens. The sky at 1 trillion years is not just empty. It is misleading. Part 4. The universe loses its own history. Almost everything known about the origin of the universe rests on 3 observations. They are independent of one another. They were established at different times by different methods, and together they form the foundation of modern cosmology. Remove any one of them, and the picture weakens considerably. Remove two, and it becomes very difficult to defend at all. The first is that distant galaxies are receding, and that the rate of recession is proportional to distance. This is the observation that established that the universe is expanding, and it carries an immediate implication when run backward. If everything is moving apart now, everything was closer together before, and there is a moment in the past when the separation approaches zero. The expansion is the single most important piece of evidence that the universe had a beginning. The second is the background of microwave radiation. Its existence was predicted before it was found, as a necessary consequence of a hot early phase, and when it was detected, it matched the prediction closely. Its temperature is uniform to a remarkable degree across the whole sky, with faint variations that encode the density fluctuations from which every structure in the universe eventually grew. It is not merely evidence for a hot beginning. It is a direct image of it, arriving late. The third is the abundance of the lightest elements. In the first minutes of the universe, when the temperature and density were high enough for nuclear reactions, but the conditions were changing rapidly, a specific set of light nuclei was produced in specific proportions. Those proportions can be calculated from known physics and compared against what is actually measured in the oldest material available. They match, which is a demanding test to pass. At 1 trillion years, the first two of these are gone. There are no distant galaxies to measure. There is nothing beyond the merged local galaxy that can be seen at all, so there is no recession to detect, no relationship between distance and velocity to discover, and no expansion to infer. Every object visible from that future galaxy is bound within it, and bound objects do not recede. An astronomer there, measuring the motions of everything they can see, would find a stable system with no expansion anywhere in it. There is no detectable background radiation. It has stretched past any wavelength that could be captured, cooled past any temperature that could be registered. The most informative single signal in cosmology becomes, from the inside of that future, indistinguishable from the absence of a signal. So consider what such an astronomer actually has to work with. They have one galaxy. It contains a great many stars, and those stars can be studied in detail, their compositions, their motions, their ages, their orbits. Around some of them there are planets, and those can be studied too. The galaxy has a structure that can be mapped, a mass that can be weighed, a center that can be examined. It is a rich subject and would support a great deal of good science. Beyond its edge, there is nothing whatsoever. No faint smudges at the limit of the largest instrument. No background glow. No signal at any wavelength. The darkness between the stars at the outskirts continues outward without feature, as far as anything can look, forever. The reasonable conclusion from that evidence is that the universe consists of one island of stars, surrounded by empty space, and has done so for as long as it has existed. There is no reason to suspect expansion. There is no reason to suspect a beginning. There is no reason to suspect that anything ever existed outside the galaxy, because there is no trace of anything having done so. A careful, rigorous, well-equipped astronomer, reasoning correctly from the best available evidence, would conclude that the universe is static and eternal, and that they can see all of it. They would be wrong. They would also be doing everything right. And here is the part that makes this genuinely strange rather than merely sad. That conclusion, one island of stars in an eternal void, is very close to what astronomers on Earth believed until surprisingly recently. Before the distances to the faint spiral smudges in the sky were measured, before it was understood that those smudges were other galaxies rather than clouds within our own, the accepted picture was of a single system containing everything. It took precise measurement of the right objects to overturn it. The far future removes those objects. Cosmology returns to where it started, permanently, with no way back. Someone in that future might propose the correct answer. It is not impossible to imagine a theorist there suggesting that space might expand, that there might once have been a hot, dense phase, that there might be other galaxies beyond the reach of any instrument. But it would be a proposal with no evidence behind it and no way of gathering any. It would sit alongside every other untestable idea, indistinguishable from them, and there would be no reason for anyone to prefer it. The truth would be available as a guess and unavailable as a finding. One clue survives, and it is worth spending some time on, because it is the last remaining thread connecting that future to the beginning of everything. The third pillar, the abundance of light elements, does not depend on looking outward. It depends on measuring what things are made of, and that measurement can be made from anywhere. And it produces a result that does not fit. Roughly a quarter of all ordinary matter in the universe, by mass, is helium. That is a great deal of helium. Stars make helium, of course. It is the direct product of hydrogen burning, which is what most stars spend most of their lives doing. But when you calculate how much helium all the stars in a galaxy could have produced across its entire history, and how much of it could have been returned to the general material rather than locked away in remnants, the number falls well short. There is more helium than stars can account for. More tellingly, the shortfall does not go away in the oldest material. If helium were purely a stellar product, then the oldest and least processed material, the material that formed earliest, from gas that had passed through the fewest generations of stars, should contain very little of it. Instead, there is a flaw. No matter how primitive the material, the helium fraction does not fall below roughly a quarter. Something put it there before any star existed. There are other threads of the same kind, fainter but pointing the same way. There is a particular heavy form of hydrogen that stars destroy but never create, and yet it is present. There is a light metal whose abundance follows a pattern that stellar processing does not explain. Each of these is a small chemical anomaly, measurable in a laboratory, requiring no telescope at all. So the last surviving evidence that the universe had a beginning is not a light in the sky. It is a ratio. It is a stubborn proportion in the composition of ordinary matter, sitting quietly in the material of that future galaxy, demanding an explanation that nothing available can supply. An anomaly with no context. A fact that is true and unexplainable at the same time. Whether anyone would read it correctly is another question entirely. It would require someone to notice that a chemical abundance is wrong, to trust that the discrepancy is real rather than an error in the models, and to reason from it all the way to a hot, dense origin for a universe that shows no other sign of having had one. It is a long inference drawn from a small clue. It might be made. It might not. There is a second thread of the same kind, less precise but perhaps more suggestive. The galaxy at that time is heavily enriched with heavy elements, carbon, oxygen, iron, everything above helium, and the degree of enrichment records how many generations of stars have lived and died to produce it. That record can be read. It tells the reader that a great many stellar generations have preceded them. What it does not tell them is anything about what came before the first of those generations, or where the original hydrogen came from, or whether there was ever anything beyond the galaxy that contained it. It is worth stepping back from the mechanics for a moment, because there is something here that goes beyond astronomy. We tend to think of knowledge as accumulating. Each generation learns more than the last, instruments improve, questions get answered, and the total store of understanding grows. Over the intervals we normally consider, that is roughly true. But the universe is not obliged to keep the evidence available. The information that makes cosmology possible is carried in light, and light has to arrive to be useful, and the arrival of light depends on conditions that are changing. What this means is that the ability to understand the universe is not a permanent feature of being an observer in it. It is a property of when you happen to be observing. There is a window during which the evidence is present and readable, and the window is not particularly wide. It opened when the first light became free to travel, and it closes when the last of that light stretches past detection. We are inside the window. Not at the beginning of it. The early universe was too hot and too opaque for anything to be seen, and not near the end. Roughly in the useful middle, at a moment when the background radiation is still measurable, the distant galaxies are still visible, the recession is still detectable, and the light element abundances can still be checked against all of it. That is a genuinely unusual position to occupy, and it is not one that anything guaranteed. The universe did not arrange for observers to appear during the readable era. It happened that the interval required for stars to form, for heavy elements to accumulate, for planets to assemble and cool and develop chemistry of any complexity, falls comfortably within the interval during which the evidence remains visible. Those two intervals did not have to overlap. They do. So the picture of that future sky is not really a picture of loss. Nothing is destroyed. The galaxies that recede continue to exist and continue to shine. The background radiation continues to travel. The beginning of the universe remains exactly as true as it ever was. What changes is only the accessibility of it, the ability of anyone inside the system to find out. And that is the quiet weight at the center of tonight's subject. Not an ending, not a darkness. A universe still full of stars, still turning, still holding worlds, in which the answer to the largest question available has simply drifted out of reach and left no forwarding address. We should turn now to what is actually shining in that sky, because the description so far has been mostly about absences, and the presences are the more interesting half. There is one further consideration worth adding here, because it changes the character of the problem in an interesting way. Information about the early universe does not only arrive as light, it also arrives as ripples in the shape of space itself, produced by violent events and traveling outward at the speed of light. These have been detected from the merging of dense remnants, and there is a long-standing expectation that a background of such ripples from the very early universe may also exist, filling space in much the same way the microwave background does. If such a background exists, it is subject to exactly the same fate. It stretches with the expansion of space, its wavelengths growing longer and its amplitude falling, until it too passes beyond anything that could be measured. The alternative channel closes alongside the first one, for the same reason, at roughly the same time. The same applies to the faint sea of neutrinos left over from the earliest moments, particles so weakly interacting that they have been streaming freely since long before light was released. They are present now, in enormous numbers, passing through everything continuously. They are also, so far, undetected directly, because their energies are too low. Over 1 trillion years, those energies fall further still, and whatever slim chance existed of catching them disappears. So it is not simply that the light goes. Every channel through which the early universe communicates with the present goes, and all of them go for the same reason, and there is no clever alternative that survives. What that leaves is only what can be measured locally, in the material at hand. The composition of matter, the proportions of the light elements, the pattern of enrichment recorded in the stars, local physics done on local objects, producing a set of numbers that hint at a history the instruments can no longer reach. There is a small consolation buried in that. The laws themselves remain available. Anyone in that future could work out how stars burn, how gravity behaves, how nuclei form and decay, how matter behaves under extreme conditions. They could derive, from first principles, that a hot, dense phase of matter would produce exactly the proportions of light elements they observe. The theory would be constructible. It would simply be unconfirmable, standing on a single anomaly, rather than on three independent measurements agreeing with each other. Whether that would be enough to convince anyone is a question about how science works, rather than a question about astronomy, and it does not have an obvious answer. Sometimes, a single stubborn discrepancy has been enough. Sometimes it has been set aside for centuries as an error in the models. There would be no way to settle it. Part 5. The stars that are left. The sky at 1 trillion years is not dark, and the reason is a class of star that almost nobody has ever seen. Not because they are rare, they are the most common kind of star in the universe by a wide margin, but because they are so faint that not one of them is visible from Earth without a telescope. Not one. Every star you can see with your own eyes belongs to a minority, and a short-lived one. These are the small red stars, the low-mass end of the main sequence, and their defining property is longevity, of a kind that requires recalibrating what the word means. A star of roughly a tenth the mass of the Sun has a main sequence lifetime measured in trillions of years. Some estimates for the very smallest run beyond 10 trillion. Against those numbers, the Sun's expected 10 billion years of steady burning is a brief episode, and the brilliant blue stars that dominate the appearance of our sky are momentary. The reason for the difference is not simply that small stars have less fuel to burn, though they do. It is that they burn what they have at an extraordinarily low rate, and that they eventually get to use nearly all of it. Both halves of that matter. The rate comes from the physics of stellar interiors. The pressure at the center of a star is set by the weight of everything above it, and in a small star, that weight is modest. Lower pressure means lower central temperature, and the rate of nuclear fusion depends very sensitively on temperature. A small reduction in temperature produces a large reduction in the reaction rate. So a star with a tenth of the Sun's mass does not produce a tenth of the Sun's light. It produces something closer to 1,000th of it. It is enormously frugal, and frugality buys time. The second half is more interesting and less widely known. In a star like the Sun, only the innermost portion is hot enough for fusion, and the material in the outer regions never reaches the core. The Sun will leave the main sequence having burned only a modest fraction of the hydrogen it contains, with most of its fuel still present and permanently out of reach. It runs out not because the tank is empty, but because the tank is badly plumbed. Small stars are plumbed perfectly. Below a certain mass, the entire star is convective. The whole interior circulates, cycling material from the surface down to the core and back again over and over. That means essentially all of the star's hydrogen eventually passes through the burning region. Nothing is stranded. A small red star consumes very nearly its entire supply at a very slow rate, and the combination of those two facts produces lifetimes that dwarf every other timescale in stellar astronomy. Now consider what this implies for the sky at 1 trillion years. Every massive star, every bright star, every star even remotely like the Sun, has been dead for an interval far longer than the current age of the universe. What remains shining is the small red population, and because that population was always the majority, there is a great deal of it. Hundreds of billions of stars. The galaxy is not sparse. It is simply dim. The quality of light in that galaxy is worth describing. These stars emit most of their energy in the infrared, with a comparatively small amount of visible light at the red end of the spectrum. A sky filled with them would be a sky of deep, warm, orange-red points, with none of the blue-white brilliance that dominates our own night sky. The overall illumination would be low. If human eyes were there to see it, the sky would look softer and darker and considerably redder than anything in the present universe. Something else is happening around that date, and it is the one genuinely new event in the entire span we are describing. Everything else in this video is a subtraction: galaxies leaving, star formation ending, remnants accumulating. This is the one addition, and it is a kind of star the universe has never yet produced. When a fully convective star finally exhausts its hydrogen, it does not behave the way larger stars do. The Sun, at the end of its main sequence life, will swell enormously and cool at the surface, becoming a red giant. That expansion happens because of the layered structure of its interior, with a spent core and a burning shell around it. A fully convective star has no such layering. It has burned its fuel uniformly throughout, so when the hydrogen runs low, the star simply contracts. Contraction heats it. The surface shrinks and grows hotter, and the color shifts from red toward blue. The star becomes brighter and bluer as it dies, the exact opposite of what larger stars do. This is a blue dwarf, and no blue dwarf has ever existed. The universe has not been around long enough for even one small star to reach that stage. Somewhere around the interval we are describing, the first of them begin to appear. There is something quietly remarkable about that. At the moment when the sky has emptied of everything external, when star formation has effectively ended, when the universe has finished doing nearly everything it does, that is the moment when it produces a kind of object it has never produced before. A new phenomenon, appearing for the first time, in a sky with almost nobody left to notice it. The blue phase does not last, by the standards of these stars, which is to say, it lasts a very long time by any other standard. Eventually the star exhausts what it has, contraction can no longer maintain the temperature, and it settles. There is no red giant phase. There is no shell of gas blown off into space, no glowing nebula, none of the ornamental death that larger stars produce. The star simply shrinks quietly into a dense remnant, rich in helium, and begins to cool. That absence is worth noting because it has a consequence for the galaxy. The bright shells of gas that dying medium-mass stars produce are one of the main ways material gets returned to the interstellar medium, where it might eventually form new stars. Small stars do not do this. When a small star ends, its material is locked away permanently. Nothing comes back. Every small star that dies represents a permanent subtraction from the galaxy's usable supply. There is a further point about these stars that connects to the parts ahead. Because they are so long-lived, and because they are so numerous, they represent the overwhelming majority of all the stellar lifetime that will ever exist in the universe. If you added up every star year that has been lived so far, and every star year that ever will be, the total would be dominated almost entirely by small red stars in the far future. The bright, brief, spectacular stars that fill our sky and our images account for a negligible fraction of it. Which means, in a plain sense, that the universe we live in is not typical of the universe. Our sky is unrepresentative. The characteristic star is not the Sun, and certainly not the bright blue giants of the nearby arms. The characteristic star is small, red, faint, and old, and the characteristic sky is the one at 1 trillion years, dim, uniform, unchanging, and surrounded by nothing. We happen to be looking during the brief and unusual interval when it does not look like that yet. Part 6. The end of making new things. Before we go further into that future galaxy, it is worth gathering what has been established, because the picture has several pieces now and they fit together in a particular way. The local group of galaxies is bound and stays. It finishes merging into a single smooth elliptical galaxy within about the first tenth of the interval we are describing, and then changes very little for the remaining 900 billion years. Everything not bound to that system recedes, crosses a horizon, and becomes permanently unobservable, a process that completes early and stays completed. The background radiation from the early universe stretches past detection, taking with it the last external signal of any kind. What remains is one galaxy in a featureless dark, holding a population of small red stars that will burn for 100 times longer still, with the evidence of its own origin reduced to a chemical anomaly in the composition of ordinary matter. That is the sky. Now we can ask what it still does. The answer is that it makes almost nothing new, and the reason is a fuel economy that has been running down since long before the Earth existed. Star formation across the universe peaked a long time ago. The rate at which new stars are made reached its maximum roughly 10 billion years in the past, when galaxies were richer in cold gas, more compact, and colliding with each other far more often. Since then, the rate has fallen steadily. The universe today produces new stars at a small fraction of the rate it managed at its peak, and the decline continues. The cause is straightforward and irreversible. Stars form from cold gas, and cold gas is a finite resource that each generation of stars partially destroys. When a cloud collapses to form stars, some of that material ends up in objects that will eventually give it back. Massive stars that explode, medium stars that shed their outer layers. But a substantial fraction is locked permanently into remnants that never return anything. Every generation of stars takes gas out of circulation and does not fully replace it. The gas that does come back is not the same gas. It has been heated, and hot gas resists collapse. It has too much internal pressure to fall together under its own weight. It has to cool before it can form stars again, and cooling is slow, particularly in a galaxy with no dense structures to help it along. Each cycle returns less material in a less usable state. In an elliptical galaxy, this problem is considerably worse. A spiral disk is an excellent machine for making stars. It is thin, it rotates, and the rotation generates density waves that sweep through and compress the gas repeatedly. Those compression waves are the spiral arms, and they are where new stars are born. An elliptical has no disk and no waves. What gas it retains sits in a hot, thin halo spread through the whole system, and it has nothing to compress it. It simply stays hot and stays diffuse. So by the date we are describing, star formation in the ordinary sense has ceased. Not slowed, ceased. There is no cold, dense gas left in usable quantities, and no mechanism to produce more. The galaxy contains the stars it contains, and it will not be adding to them in any way that a large-scale survey would notice. It does add to them occasionally, though, and the exceptions are worth describing because they are the only genuinely new light produced in an otherwise fixed system. The first exception involves objects that did not quite manage to become stars in the first place. Below a certain mass, a collapsing cloud of gas cannot generate enough central pressure to sustain hydrogen fusion. It contracts, warms, glows faintly from the heat of its own contraction, and then cools slowly for the rest of time. These are brown dwarfs, and they are extremely numerous. The low-mass end of the formation process produces a great many objects that fall just below the threshold. They also persist. A brown dwarf does not burn out because it never burned. It simply cools, and cooling takes an enormous length of time. Over 1 trillion years, the galaxy accumulates a large population of them drifting on their own orbits through the general stellar swarm. And over long enough intervals they collide. Not often, the space between them is enormous and the encounters are rare, but a galaxy contains a great many of them, and 1 trillion years is a great deal of time. When two brown dwarfs merge, the combined mass may cross the threshold that neither could reach alone. The merged object contracts, its center reaches the required temperature, and fusion begins. A new star lights up in a galaxy that stopped making them long ago. There is something appealing about that image. Two objects that each failed to become a star, drifting separately in the dark for 1 trillion years, meeting by chance and succeeding together. The resulting star is small and red and will burn for trillions of years more, in a galaxy that has otherwise finished. The second exception involves the remnants of stars that did burn. White dwarfs, the cooling cores of medium-mass stars, are also numerous and also drift. When two of them meet, the outcome depends on the combined mass. Sometimes they merge into a single larger remnant. Sometimes the combination exceeds a critical limit, and the merged object cannot support itself. It collapses, ignites in a runaway burning of its material, and destroys itself in a brief and brilliant event, visible across the galaxy. These are rare in the extreme by that stage, and they are brief. A single such event might illuminate the galaxy for a few weeks and then fade, leaving nothing but expanding debris and a somewhat richer interstellar medium. Across 1 trillion years, there might be a scattering of them, separated by intervals so long that each one is effectively an isolated occurrence, with nothing before or after it. What this amounts to is a galaxy that has moved from a process to a state. Through the first part of its history, it was doing something, assembling, forming, enriching, merging, building. By 1 trillion years, it is simply being. The stars it has are the stars it will have. The material is distributed as it will remain distributed. The occasional new light is punctuation in a text that is otherwise finished. There is one more consideration that belongs here, and it concerns what all this means for the total amount of light in the universe. The galaxy at 1 trillion years produces vastly less light than a galaxy does today, for two reasons that compound. It has no bright stars, because bright stars are short-lived and none have been made for a very long time. And it has fewer stars overall, because the population has been declining as small stars gradually reach the ends of their own very long lives. The decline is gentle. Small stars die slowly and rarely, so the galaxy dims by a small amount over enormous intervals rather than fading noticeably. To anyone living inside it, at any point across hundreds of billions of years, the sky would appear entirely unchanged. The dimming is real, and it is happening, and it is far too slow for anything to notice. That is a fair description of the whole era. Real processes running steadily, at rates so slow that from inside the system, nothing appears to be happening at all. The galaxy at 1 trillion years is not static. It is only patient beyond any useful comparison. There is a further consequence of the exhaustion of cold gas that deserves attention because it concerns not the making of stars, but the making of everything else. Planets form from the same material as stars, in the disks of gas and dust that surround stars as they assemble. No gas means no disk, and no disk means no planets. So the end of star formation is also the end of planet formation, and it arrives at the same time and for the same reason. Every rocky world that will ever exist in that galaxy already exists by the date we are describing. Every ocean, every atmosphere, every surface that could ever be stood on has already been assembled. The inventory is closed. What is there is what there will be, minus whatever is gradually lost to collisions and ejections over the following intervals. This is a strange thought to hold alongside the previous one about habitability. The best conditions for life around small red stars lie in the far future, long, calm, magnetically quiet, stable across trillions of years. But the worlds that would host those conditions have to have been built already, during the brief early era when there was still gas to build them from. The opportunity and the material arrive at different times, and only the worlds that were made early enough get to take part. There is something similar to say about heavy elements. The material that rocky worlds are made of, silicon, iron, oxygen, magnesium, is produced in stars and returned to the interstellar medium when they die. The abundance of those elements climbed steadily through the galaxy's history, which means that later generations of planets were built from richer material than earlier ones. By the end of star formation, that enrichment reaches its highest level, and the last worlds to form are the most heavily supplied with the elements that make a world interesting. They are also the last ones. The galaxy achieves its best planet-building material at the moment it stops building planets. It is worth noting a limit on all this because the picture can be pushed too far. Gas exhaustion is not absolute. There are always trace amounts, always some material being returned, always the possibility that a local concentration collapses under unusual circumstances. The claim is not that nothing forms ever again. The claim is that the process, considered across the galaxy as a whole, has fallen to a rate low enough that it no longer shapes anything. What was once the defining activity of a galaxy becomes an occasional accident. Part 7. The slow accumulation of the cold. Every star that has ever finished burning has left something behind, and none of those things go away. Over 1 trillion years, the galaxy accumulates them steadily, and by the date we are describing, they outnumber the stars still shining. The future galaxy is, numerically, a population of cold remnants with a scattering of small red stars living among them. The most common of these remnants is the white dwarf, and it is worth understanding properly because it is the dominant object of the far future. A white dwarf is what remains when a star of moderate mass finishes fusion. The outer layers are shed, drifting outward as an expanding shell, and what is left is the core, the dense, hot, exhausted center of the star, exposed. The physical situation is unusual. A white dwarf holds something close to the mass of the Sun in a body roughly the size of the Earth. Nothing is burning inside it. There is no energy source at all. What holds it up against its own gravity is not pressure from heat, as in a normal star, but a quantum mechanical resistance of the electrons themselves to being packed more tightly. That resistance does not depend on temperature, which means the object can cool indefinitely without collapsing. So, a white dwarf simply radiates. It has a large reservoir of heat left over from when it was the core of a star, and it gives that heat away into space, slowly, for as long as it exists. It does not shrink as it cools. It only dims and reddens. The cooling is remarkably slow, and the reason is geometry. Radiating heat requires surface area, and a white dwarf has very little of it. A star's worth of mass wrapped in a planet's worth of surface. The heat leaks out through a small opening, so to speak, and the process takes an extraordinary length of time. Cooling to genuine darkness, to a temperature indistinguishable from the surrounding space, takes far longer than 1 trillion years. The relevant timescale runs into the quadrillions. This produces one of the more interesting features of the date we are describing. At 1 trillion years, white dwarfs are not black. The truly cold remnant, the fully dark object with no residual heat at all, is a thing the universe has not yet had time to make, even at that date. What exists instead is an enormous population of very cold, very faint objects, still radiating a small amount, still detectably warmer than the space around them. They are dim past visibility, but not past existence. Our own sun is one of them. Its remnant, by that date, will have been cooling for something like 1,000 times longer than the sun spent shining. Its surface will be colder than any planetary surface in the present solar system, colder than the outer moons, colder than the material at the far edge of the sun's influence. It will still be there, still holding nearly half the mass the sun had, still leaking a trace of heat into a sky with nothing in it. Whether anything still orbits it is a separate question, and an interesting one. Some of the outer planets very likely survive the Sun's red giant phase, pushed into wider orbits as the Sun loses mass. Those orbits are stable over enormous intervals. It is entirely plausible that 1 trillion years from now, there are still worlds circling the cold remnant of the Sun, on slow orbits, in permanent dark. The second class of remnant is denser and rarer. When a star well above the Sun's mass reaches the end of its life, the core collapses further than the electron resistance can prevent, and the collapse continues until the matter reaches the density of an atomic nucleus. What remains is a neutron star, something like the mass of the Sun compressed into a sphere a few kilometers across, so dense that a spoonful of its material would weigh as much as a mountain. Neutron stars are born spinning rapidly and carrying magnetic fields of enormous strength. Many of them are detectable from great distances as regular pulses of radiation sweeping past like a beam. But rotation is energy, and radiating that energy costs rotation. The magnetic field acts as a brake against the surrounding material, and the star spins down steadily over its lifetime. Over 1 trillion years, that process finishes. The rotation slows from fractions of a second to seconds to minutes and beyond. The magnetic fields decay. The surface, initially at temperatures of hundreds of thousands of degrees, cools toward the background. What was a beacon becomes a dark, dense, slowly turning object, indistinguishable at a distance from any other cold mass. The third class does not change at all, and its permanence is worth dwelling on. Black holes formed from the collapse of the most massive stars are entirely unaffected by the passage of 1 trillion years. There is a process by which they lose mass, a very slow radiation associated with the behavior of quantum fields near the horizon. But for a black hole of stellar mass, the timescale for complete evaporation is a number with something like 67 zeros in it. Against that, 1 trillion years is not a small interval. It is no interval at all. It does not register. So the black holes of that future galaxy are precisely the black holes that formed hundreds of billions of years earlier, unchanged in every respect. They drift on their orbits, occasionally passing near enough to a star to disturb it, occasionally consuming material that comes too close. They are among the most permanent objects the universe produces. At the center of the merged galaxy sits the largest of them, the combined supermassive object formed when the central black holes of the two original spirals joined. It grew substantially during the merger, fed by gas driven inward by the encounter, and then it ran out of things to eat. By the date we are describing, it has been quiet for the better part of 1 trillion years. Occasionally a star wanders close enough to be pulled apart, producing a flare of radiation as the debris falls in. Those events are rare and brief. Most of the time, the center of the galaxy is simply a very large concentration of mass, doing nothing. There is a fourth category that is not exactly a remnant and deserves a mention. Brown dwarfs, described earlier, never burned in the first place. They cool from their formation heat and continue cooling indefinitely, becoming steadily colder and fainter, without any dramatic transition. By 1 trillion years, they are cold objects, in some cases colder than the surface of a planet, drifting on stellar orbits through the galaxy. There are a great many of them. Add all of this together, and the composition of the future galaxy becomes clear. The great majority of its objects are dark, or nearly so. Cold white dwarfs, cooled neutron stars, black holes, brown dwarfs, and free-floating planets make up the bulk of the population. Among them, spread thinly, are the small red stars still burning, a minority in number and the only source of light in the entire visible universe. It is worth resisting the instinct to describe this as a graveyard, because the word carries connotations that do not fit. Nothing about that galaxy is decaying or falling apart. The white dwarfs are stable, and will remain so for periods that make 1 trillion years look brief. The black holes are the most durable objects that exist. The remaining stars are burning steadily and will continue for 100 times the interval already elapsed. It is a settled system, not a ruined one. There is also a gravitational consequence worth noting. As more of the galaxy's mass ends up in compact objects rather than in extended stars, the system becomes, in a sense, more granular. Encounters between objects become the dominant way that energy moves through the system, rather than the smooth gravitational field of a distributed population. This has slow effects on the structure of the galaxy that we will come to shortly. And there is one more feature of that population that seems worth mentioning simply because it is unexpected. The white dwarfs, cold as they are made of matter under conditions that occur nowhere else. At those densities and those temperatures, the material eventually stops behaving like a fluid and settles into an ordered arrangement, the atomic nuclei arranging themselves into a regular structure held rigid by their mutual repulsion. The interior of an old white dwarf is, in a meaningful sense, crystalline. This has been detected in stars that exist now, appearing as a delay in the cooling as the process releases a little heat. Over 1 trillion years, that process completes throughout the population. Essentially, every white dwarf in the galaxy is a solid, ordered, cold object of a kind that has no counterpart anywhere else in nature. They are the most numerous large objects in the universe by that date, and they are all quietly the same. Part 8. Worlds in the long evening. Planets are more durable than stars, and this is not a fact that gets much attention. A star has a defined lifetime because it is consuming something. A planet is not consuming anything. It has no fuel to run out of, and nothing in its ordinary operation that terminates. Left undisturbed, a rocky world simply persists, orbiting, cooling gradually, but structurally intact for as long as its star holds together, and often long after. Around the small red stars that populate the future galaxy, this produces a situation that has no equivalent in the present universe. A world orbiting such a star can remain there, in a stable orbit, receiving steady warmth for the entire lifetime of the star. Which is to say, for trillions of years. Not for the few billion years that a world around a star like the Sun is granted, but for a period longer than the entire history of the universe up to now, many times over. The geometry of such a system is worth describing because it is quite different from ours. A small red star is faint, which means the region where a world would receive enough warmth for liquid water sits very close in. Instead of orbiting at a distance measured in tens of millions of kilometers over a period of a year, a world in that position orbits at a few million kilometers over a period of days or weeks. Its year is shorter than our month. Orbiting that close has a consequence. The gravitational pull of the star on the near side of the world is noticeably stronger than on the far side, and that difference acts as a brake on the world's rotation. Over time, the rotation slows until it matches the orbit exactly, and the world keeps one face permanently toward the star. This is tidal locking, and it is the expected condition for almost any world in the warm zone of a small red star. The result is a world with 3 permanent regions rather than a cycle of day and night. On one side, perpetual daylight, with the star fixed in the sky at the same position forever, never rising, never setting, never moving. On the opposite side, perpetual night, with no star in the sky at all. And between them, encircling the world, a permanent band of twilight where the star sits exactly on the horizon and stays there. That terminator band is a genuinely strange environment to think about. The light arrives at a permanent grazing angle, so every object casts a shadow that never shortens or lengthens or changes direction. The temperature is intermediate between the hot face and the frozen one, and moderated further by whatever atmosphere and circulation the world has. Conditions there could be remarkably stable, not stable for centuries, but stable for hundreds of billions of years. There is a complication with small red stars in their youth, and it deserves an honest mention. Young stars of this class are magnetically violent. Their fully convective interiors generate strong fields, and their rapid rotation drives those fields hard. The result is frequent, powerful flares, outbursts that, relative to the star's ordinary output, are far larger than anything the Sun produces. A close orbiting world would be exposed to these repeatedly, and there is a real question about whether an atmosphere could survive that treatment. But this is a phase, and that fact changes the entire picture when the timescales are considered. Magnetic activity in these stars is driven by rotation, and rotation slows over time as the star's magnetic field interacts with the material around it. As the star spins down, its magnetic activity subsides. The flares become less frequent and less energetic. Eventually, the star settles into a long, quiet, magnetically calm maturity. The interval of violence lasts perhaps a few billion years. The interval of quiet that follows lasts trillions. So the difficult period, which dominates every present-day discussion of whether such worlds could be hospitable, occupies a fraction of a percent of the star's life. By the date we are describing, every surviving small red star has been magnetically quiet for something close to 1 trillion years. This produces a conclusion that seems worth stating clearly. The longest, calmest, most stable conditions available anywhere in the history of the universe are not in the past and are not now. They are ahead. If worlds around small red stars can support anything at all, the best circumstances for it are in the far future, orbiting stars that have long since settled, under skies that never change. There is a further class of world in that future, and it is more numerous than the ones with stars. Planets are frequently ejected from the systems that form them. Young planetary systems are gravitationally chaotic. Worlds interact, exchange energy, and occasionally one is flung out entirely on a path that never returns. Over the history of a galaxy, this happens a great many times, and the ejected worlds accumulate. These free-floating planets drift through the galaxy on their own orbits, belonging to nothing. They have no star, no illumination, no external source of warmth. Their surfaces cool toward the temperature of the space around them, which by that date is very close to absolute zero. But their interiors are a different matter. A rocky world of reasonable size contains radioactive elements in its interior, and the decay of those elements produces heat continuously. That heat takes an enormous length of time to escape, because rock is a poor conductor and the world is large. A free-floating planet can retain a warm interior for an extraordinarily long period after its surface has frozen solid. If such a world carries a sufficient layer of ice, that internal heat can maintain liquid water beneath it. This is not speculative in principle. It is the arrangement found on several moons in the present solar system, where subsurface oceans persist beneath ice shells warmed from below. A free-floating planet with the right composition could carry an ocean under its ice through the whole of the interval we are describing, entirely independent of any star, in complete and permanent darkness. There is something remarkable in that. The most durable liquid water in the universe might not be on any world with a sky. It might be under kilometers of ice, on planets with no stars, drifting between the cold remnants of a galaxy that has forgotten where it came from. There is a third arrangement, and it is the strangest of the three. Some worlds orbit white dwarfs. This can happen in more than one way. An outer planet that survived its star's expansion and settled into a new orbit, or a world that migrated inward afterward, or debris that reassembled. Whatever the route, planets around white dwarfs exist now and have been detected. A world orbiting a cold white dwarf occupies an unusual position. The star gives out a small, absolutely steady amount of heat, declining so gradually that over any interval that matters, it is effectively constant. There are no flares, because there is no magnetic activity to drive them. There is very little ultraviolet radiation, because the remnant is too cool to produce much. It is the most placid energy source available anywhere. The warm zone around such an object is extremely close in, and a world there would orbit in hours rather than days. It would be tidally locked, as before. But it would sit in a light that never varies, from a source that will not change for longer than the current age of the universe, with nothing else in the sky at all. And that is worth pausing on. The sky above any of these worlds, the tidally locked world at its red star, the ice-covered drifter, the close companion of a cold remnant, contains no other galaxies. It contains no background glow. It contains the stars of the local galaxy, dim and red and unmoving, and beyond them, nothing whatsoever. It is a sky in which essentially nothing happens, and in which essentially nothing has happened for hundreds of billions of years. For a listener, that might sound bleak, and it is worth saying why it might not be. Change is what makes a sky interesting to us, but change is also what makes it precarious. The skies we know are full of things that are ending. Every bright star we can name is burning down. Every galaxy we can see is on its way out of reach. The sky at 1 trillion years has none of that. Whatever it holds indefinitely. It is the most stable configuration the universe ever arrives at, while still containing light. The most peaceful skies that have ever existed or ever will exist are the ones nobody has seen yet. A small red star that never flares, a world that never turns, and a night that has nothing left to lose. It is worth adding something about time as it would be experienced in such a system, because the numbers involved change the meaning of ordinary words. A world orbiting a small red star in its warm zone completes an orbit in a matter of days. Over the lifetime of that star, it completes something on the order of 100 trillion orbits. For comparison, the Earth has completed roughly 4.5 billion orbits since it formed, and will manage perhaps 10 billion in total before the Sun ends the arrangement. The difference is not a matter of degree. Nothing about the world would change across most of that. There are no seasons on a tidally locked planet, because seasons require a tilted axis and a varying distance from the star, and a locked world has neither in any meaningful sense. There is no day and no night. The star does not rise or set. The only variation available is weather, driven by the permanent temperature difference between the lit face and the dark one, and whatever slow geological activity the interior can sustain. Geological activity is the interesting question there, and it has a limit. The heat that drives the interior processes of a rocky world comes partly from its formation and partly from the decay of radioactive elements within it. Both supplies deplete. The formation heat leaks away over hundreds of millions to billions of years. The radioactive supply falls as the elements decay, halving repeatedly, until the heat production becomes negligible. For a world like the Earth, that process is well advanced already. Over 1 trillion years it goes to completion. The interior cools, the movement of the outer layers stops, and whatever geological renewal was occurring ceases entirely. The surface becomes fixed. Whatever features exist at that moment remain, without erosion by tectonics, without renewal, without change, for as long as the world lasts. That produces a curious kind of permanence. A landscape on such a world, at the moment its interior finishes cooling, is a landscape that stays. Not for millions of years, which is what we mean by permanent when discussing terrain on Earth, but genuinely, the same arrangement of rock, under the same fixed star, in the same fixed light, for a period longer than the entire history of the universe up to now. There is a further point about the atmospheres of these worlds. Over enormous intervals, gases escape. Light molecules leak away from the top of an atmosphere continuously, and the loss accumulates. Whether an atmosphere survives 1 trillion years depends on the mass of the world, the temperature at the top of its atmosphere, and the composition of the gas. Heavier worlds hold on better. Cooler worlds hold on better. Some would keep their atmospheres for the whole interval. Some would lose them slowly and end as bare rock under a red star. The distribution across the population would be wide, and there is no single answer that covers all of them. What can be said is that the timescale for atmospheric loss and the timescale for stellar lifetime are, for these systems, comparable. In our system, the Sun ends the story long before the atmosphere would have leaked away. Around a small red star, the two processes run in the same range, and a world's fate depends on which of them gets there first. Part 9. The shape of the last galaxy. Having described what the galaxy contains, it is worth describing what it looks like as an object and how it holds itself together across an interval that long. The merged galaxy is an elliptical, which means its stars are arranged in a smooth, roughly spheroidal distribution rather than a flat disk. The density is highest at the center and falls away gradually outward, with no sharp edge anywhere. There is no plane, no preferred direction, no rotation of the system as a whole in the way a spiral rotates. Individual stars orbit the center on paths tilted at every possible angle, in every possible direction, and the sum of all those motions largely cancels. This is a fundamentally different kind of dynamical system from the one we live in, and the difference has consequences. In a spiral galaxy, the stars in the disk all travel in the same direction at similar speeds, which means their relative velocities are low and encounters between them are gentle. In an elliptical, stars on randomly oriented orbits pass each other at high relative speeds and from all directions. The system is hotter, in the sense that the random motions are larger, even though the total energy is comparable. Holding all of it together is a halo of dark matter, and this deserves attention because it is one of the very few things about the galaxy that is essentially unchanged from the present day. Dark matter does not burn because it does not participate in the interactions that make burning possible. It does not cool because it does not radiate. It does not clump into stars or planets or remnants. It simply provides gravity, distributed through a roughly spherical region extending far beyond the visible stars, and it will go on doing exactly that for as long as the universe lasts. The visible galaxy sits inside that halo like a bright core inside a much larger invisible structure. Most of the mass of the system is in the halo rather than in anything that shines. This is true now, and it remains true then, and if anything it becomes more pronounced, because the visible component dims while the halo stays the same. Now, over very long intervals, something begins to happen to the stellar population, and it is the slowest structural process in the whole video. When two stars pass near one another, they exchange a small amount of energy gravitationally. One speeds up slightly, and one slows down slightly. Any single encounter is negligible. But the galaxy contains hundreds of billions of stars, and over 1 trillion years there are a great many encounters. The cumulative effect is a slow redistribution of energy through the system, a process astronomers call relaxation. It has a characteristic outcome. Some stars, through a long series of favorable encounters, gain enough energy to move onto wider and wider orbits, and eventually a few gain enough to leave the galaxy entirely. Others lose energy in the exchange and sink toward the center. The galaxy slowly evaporates from the outside while concentrating at the middle. That process is real, and it does eventually dissolve galaxies. The timescale is the important part. It runs to something in the region of tens of quintillions of years, which is to say 10 million times longer than the interval we are describing. At 1 trillion years, relaxation has barely begun. A handful of stars have been ejected. The central concentration has increased by an amount that would be difficult to measure. The galaxy is, for all practical purposes, exactly as it was when the merger finished. This is a useful thing to hold on to, because it clarifies what kind of moment 1 trillion years actually is. Every process that shapes the appearance of the sky has either finished or barely started. The merging is finished. The emptying is finished. Star formation is finished. Relaxation has not meaningfully begun. Black hole evaporation has not begun in any sense at all. The galaxy sits in a long interval between the processes that built it and the processes that will eventually take it apart, and that interval is the longest stretch of stability in the history of the universe. The material between the stars is worth a brief description because it has changed character considerably. The interstellar medium of the present galaxy is a mixture of cold, dense clouds, warm, diffuse gas, and hot, rarefied material, with the cold component being where stars form. In the future galaxy, the cold component is essentially gone. What remains is a thin, hot, low-density gas filling the space between the stars and extending out through the halo. That gas is enormously enriched in heavy elements compared with what the Sun formed from. Every generation of stars that has lived and died has contributed material, carbon and oxygen from the shed layers of medium stars, iron and heavier elements from the explosive deaths of larger ones. The proportion of everything above helium has climbed steadily throughout the galaxy's history. By that date, it is many times what it was when the solar system formed. This has an interesting implication that connects back to the earlier discussion. That enrichment is a record. It is written into the composition of every object in the galaxy, and it can be read. Anyone studying the material of that future galaxy could determine that a great many generations of stars have preceded them, and could reconstruct a good deal about what those stars were like from the pattern of elements they left. The stellar history of the galaxy is recoverable. It is only the history before the stars that is not. The center of the galaxy deserves a final visit. The supermassive black hole there is the largest single object in the system, and it is surrounded by a dense concentration of stars on tight orbits. Those stars have survived everything, the merger, the burst of star formation, the long decline, because they are small, and small stars endure. They orbit at high speed around a mass that gives out no light in the densest stellar environment the galaxy contains. Occasionally, one of them is disturbed onto a path that carries it too close. The tidal forces near a black hole of that size are strong enough to pull a star apart, stretching it into a stream of material that partly falls inward and partly escapes. The infalling material heats as it spirals in and produces a flare of radiation, bright for a period of months, then fading. By the date we are describing, these events are rare. The supply of stars on disturbable orbits has been gradually depleted, and the mechanisms that resupply it operate slowly. But they still happen, and each one is by a considerable margin the brightest thing that occurs in the observable universe during the interval surrounding it. A flare at the center of the only galaxy there is, illuminating a sky with nothing else in it, and then fading back to the ordinary dim red. The outer boundary of the galaxy is not a boundary in any physical sense. The density of stars falls away gradually, thinning through the halo, until there are simply no more. There is no wall, no edge, no last star that marks the end. There is only a region where the count per unit volume declines toward zero. And beyond that region, nothing. Not sparse space with distant objects in it, which is what the space beyond our galaxy looks like now. Genuinely nothing. No detectable radiation of any wavelength, no particles arriving from outside, no faint smudges at the limit of resolution. The galaxy's outskirts fade into a dark that contains no information at all and continues without feature in every direction. The edge of that galaxy is the edge of the knowable universe, and the two coincide exactly. That has never been true before, and it will remain true from then on. There is one more structural feature of that galaxy worth describing, and it concerns the halo rather than the bright interior. The visible galaxy sits inside a much larger distribution of dark matter, but it also sits inside a distribution of ordinary matter that never made it into stars. This is the hot, thin gas of the halo, spread through a region far larger than the stellar body, and it contains a substantial fraction of the ordinary matter belonging to the system, in some accountings more than the stars themselves. That gas has never been usable. It is too hot and too thinly spread to collapse, and there is no process available to cool it efficiently. Over the history of the galaxy, it has been added to repeatedly by material driven outward from the disk during energetic episodes and by gas stripped from smaller galaxies as they fell in. It accumulates and it stays. So the future galaxy is, in terms of ordinary matter, mostly gas that never became anything. A large hot halo, a smaller population of stars and remnants embedded within it, and a much larger dark matter halo containing all of it. The bright part, the part that would be visible in an image, is a minority component in every respect. There is an aesthetic point to be made about that which is worth a moment. Galaxies in images look like objects with edges, bright structures against a dark background. That impression is a product of what emits light. The actual object extends far beyond anything visible, in every direction, made of material that gives out nothing. What we call a galaxy is the small, luminous core of something considerably larger and almost entirely dark. That was true at the beginning, and it remains true at the end. One more dynamical detail belongs here, because it concerns the black holes. Over long intervals, the massive compact objects in a galaxy tend to sink toward the center. When a heavy object moves through a field of lighter ones, it disturbs them gravitationally and leaves a slight overdensity in its wake, which pulls back on it. The effect is a steady drag, and it drains orbital energy from the heaviest members of the population. Black holes, being the heaviest things in the system, are the most affected. Over 1 trillion years, a substantial number of them will have migrated inward, concentrating toward the center of the galaxy. Some will have reached the central region and joined the supermassive object there. Others will orbit in the dense inner zone, a population of dark, heavy objects gathered around a much darker, heavier one. That concentration is a slow, quiet, entirely gravitational process, producing no light and no event that anyone could observe. It simply happens, over intervals long enough that the arrangement of the galaxy's heaviest objects at the end bears little resemblance to the arrangement at the beginning. Part 10. What a night would look like. It seems worth putting all of this together into something more direct, because the description so far has been structural, and there is a view to be had. Imagine standing on the surface of a rocky world in that future galaxy, one of the tidally locked worlds around a small red star, on the twilight band where the star sits permanently on the horizon. Look away from the star, toward the night side, and consider what is in that sky. The star itself, behind you, is not the star we are used to. It is smaller in the sky than the sun appears from Earth, despite being much closer, because it is a much smaller object. Its light is deep orange, closer to the color of an ember than to daylight. It does not move. It has occupied the same position on the horizon since before the world had a surface worth standing on, and it will occupy that position long after. The sky itself, on the dark side, is not black in the way we might imagine. It holds stars, a good many of them, spread evenly across the whole hemisphere, because in an elliptical galaxy, there is no plane to concentrate them into a band. Every one of them is red or orange. There are no blue stars, no white ones, no brilliant points that outshine the rest. The brightness is uniform and low, and the overall color of the sky is warm rather than cold. There is no band of light across it. That is the thing that would be most immediately unfamiliar to a human observer. Our sky has the great arch of the galactic disk running through it, and it has been there for the whole history of every culture that has ever looked up. That structure is a product of living inside a flat, rotating system. In a spheroidal galaxy, there is nothing to produce it. The sky is featureless in the large, uniform in every direction and softly lit. There are no other galaxies. This is the deeper absence, and it is harder to picture, because from Earth, the other galaxies are not obvious either. Only one or two are visible to the unaided eye, and even those look like faint patches. But they are there, and every image taken through any instrument reveals more of them, in every direction, without limit. Point a telescope at any apparently blank patch of the sky from Earth, hold it there long enough, and thousands of galaxies emerge. Do that from the future world and nothing emerges. Hold the exposure for a year and nothing emerges. There is no faint background that resolves into structure with enough patience. The dark between the stars of the local galaxy is not full of distant things too faint to see. It is genuinely, verifiably empty. Consider what that means for anyone trying to make sense of the sky from there. Every question we currently ask about the universe at large would be unanswerable, and more than that, would not arise. There would be no reason to ask how many galaxies there are, because there would be one. No reason to ask how old the universe is, because there would be nothing to date it against beyond the stars themselves. No reason to ask what the universe is expanding into, because nothing would appear to be expanding. The questions that would arise instead would be local ones. What are the stars made of? How do they burn? Why are the cold remnants so numerous? What is the nature of the mass that holds the galaxy together but gives out no light? These are excellent questions, and they would be answerable. Astronomy would be a healthy science there. It would simply have a ceiling on it that nobody could see. There is a temporal quality to that sky as well that is worth describing. Our sky changes. Not on a human timescale in any obvious way, but it changes. Stars form and die, supernovae appear and fade, comets arrive, planets move, and over longer intervals the constellations dissolve entirely. The sky is a record of ongoing processes. The future sky does almost none of that. The stars do not form, because star formation has ended. They do not die visibly, because the deaths of small stars are slow and undramatic. There are no supernovae in the ordinary sense, because the stars that produce them have all been gone for hundreds of billions of years. The stars move on their orbits, but the orbital periods in an elliptical galaxy are measured in hundreds of millions of years, so the arrangement is stable across any interval anyone would care about. Something appears occasionally. A brown dwarf merger lighting a new star. A white dwarf collision flaring briefly and fading. A star pulled apart at the galactic center, producing a glow that lasts a season. These events are separated by intervals so long that no continuous record could reasonably connect them. Each would be, to anyone present, a singular occurrence with no precedent in memory. And then there is the quality of the darkness itself, which is different in kind from ours. The space between the stars in the present universe is not truly empty. It is filled with the background radiation from the early universe, faint but detectable everywhere, a bath of microwaves that permeates everything. Every cubic meter of space contains photons from the beginning of the universe. In a real sense, the early universe is present in this room right now, arriving continuously from every direction. In the future sky, that is gone. The background has stretched past detection. The darkness between the stars is not a warm dark filled with ancient light. It is a genuinely empty dark, containing nothing, having contained nothing for hundreds of billions of years. It seems worth being clear that none of this would feel like deprivation from the inside. That is a projection from our position, not a feature of theirs. A sky that has always been that way is simply the sky. The absence of other galaxies is only an absence if you know they should be there. What we are describing as a loss would be, to anyone actually looking up, an entirely ordinary and rather beautiful night. And it would be beautiful. A sky of soft red points, evenly spread, unchanging, under a star that never moves, over a world with no seasons and no day and no night, only a permanent gentle light on one horizon. Nothing arriving, nothing departing. The most settled arrangement the universe manages to produce while still containing anything at all. If there is a difference between that sky and ours worth naming, it is not brightness or emptiness. It is that our sky is still arriving. Light is still reaching us from things we have never seen, from distances we are still measuring, carrying information about a past we are still assembling. Every clear night is a delivery. Every deep image adds to a record that is still being written. That sky is finished. Everything that was going to arrive has arrived. The record is complete, and it is a very short record, and it is missing almost everything. Part 11, What Comes After, and the Way Back. It is worth taking one look further forward before turning around, because 1 trillion years is not the end of the story, and it would be misleading to leave it as one. The small red stars continue burning long past the date we have been describing. The largest of them begin their blue contraction phase around that interval, but the smallest and most frugal are still in the early part of their main sequence lives. They continue for what is estimated at something like 100 trillion years, 100 times the interval already covered. When the last of them finishes, the stellar era of the universe ends. That is the true close of the age of stars, and it happens at a date so much further out that the trillion-year mark, which seemed enormous when we started, becomes an early milestone. After that point, the galaxy contains no stars at all, only cold remnants, planets, brown dwarfs, and black holes, moving slowly in a dark that has no other source of light. Even then, occasional light appears. The rare collisions continue. Objects drifting for long enough will eventually meet, and some of those meetings produce brief illumination. Across intervals long enough, even the extremely improbable becomes routine. But these are isolated flares in a very long darkness, rather than anything that could be called an era of light. Beyond that, the timescales stop being useful as quantities. The slow gravitational relaxation described earlier eventually disperses the galaxy, ejecting most of its objects into the space between and leaving the remainder to fall toward the center. That happens at something like tens of quintillions of years. Black hole evaporation, the slow leakage of radiation from the horizon, becomes relevant at intervals with 60 or more zeros in them. And there is an open question, genuinely open, not merely unsettled, about whether ordinary matter is perfectly stable over unlimited time, or whether it very slowly decays. The honest position on all of that is that the physics governing those intervals has never been tested, and in some cases cannot be. We are extrapolating known laws far beyond any regime in which they have been checked. The picture at 1 trillion years rests on measured expansion, measured stellar lifetimes, and observed galaxy dynamics, all of which are on firm ground. The picture at 1 quintillion years rests on considerably less. So this is a good place to stop going forward and turn around. Everything described tonight follows from processes that are happening at this moment. The neighbouring spiral galaxy is approaching now, and the approach has been measured. The expansion is accelerating now, and the acceleration has been measured. Galaxies are crossing the horizon now, quietly, one at a time, while we speak. Objects that were observable in principle a moment ago and are not any longer. The rate of star formation is declining now. The cold gas supply is being consumed now. The future we have described is not a separate condition that begins at some point. It is the continuation of tonight, and tonight is an early part of it, which puts the present sky in a particular light. Every galaxy visible from Earth is visible because we happen to be looking during the interval in which it can still be seen. That interval is closing, slowly, and it will not reopen. The images that have been taken of the deep sky, the long exposures that reveal thousands of galaxies in a patch of apparently empty dark, are records of a condition that is temporary. The background radiation is still measurable. The recession of distant galaxies is still detectable. The light element abundances can still be checked against both. All three pillars of our understanding of the origin of the universe are still standing, at the same time available to be compared with one another. That has not always been true, and it will not always be true. It is not a small thing to be alive during the readable era. There was no arrangement that made it so. The interval required to produce observers, for stars to form, for heavy elements to accumulate through several generations, for planets to assemble and cool and develop anything complicated, happened to fall inside the interval during which the evidence remains visible. Those two spans did not have to overlap at all. They could have been separated by 100 billion years, and everything we know would have been permanently unavailable to anyone. There is a version of this that sounds like a warning, and that is not the intention. Nothing about it is urgent. The window is not closing on any timescale that concerns anybody, and no action follows from knowing about it. The galaxies will still be there tomorrow night and every night for longer than the species will exist. What follows is something gentler. It is simply worth noticing. The sky above this planet at this moment contains the answer to where all of it came from. The light carrying that answer is still arriving, has been arriving continuously since long before anything was here to receive it, and will keep arriving for a good while yet. Every clear night, that information falls on the surface of this world whether anyone reads it or not. For 1 trillion years afterward, it will still be true that the universe expanded, that it had a beginning, that it once held 100 billion galaxies. It will simply be unfindable. The truth outlasts the evidence for it, and nothing about the truth mines. So the sky we have described tonight is not a warning and not a loss. It is a version of this sky with the distant parts removed, arrived at slowly, by processes that are gentle and enormously patient. A single galaxy of soft red stars. Cold remnants outnumbering the living. Worlds under permanent twilight, orbiting stars that never flare. Ice-covered planets carrying oceans through the dark. And around all of it, a quiet that has nothing left in it to disturb. The light from the farthest galaxies is still arriving tonight, and it will keep arriving for a long while yet. Nothing that is leaving quickly, and nothing that is here now needs to be held on to. Let your breathing slow. Let the sky keep its own time. Sleep well, and good night.